Okay, so look up, if you're watching this at home, heat, gas line antifreeze. We were just looking at it in class.
Sorry.
It's okay. Come on in. And we were talking about how the bottle of heat looks like a bottle of Yoo-hoo, but not to us because we're grown-ups. But I have a story to tell y'all. In my hometown, when I was in middle school, I had a friend that had a younger brother, and he was a toddler, and he saw the bottle of heat in his dad's shop. Well, to a toddler, the bottle of heat looked like a bottle of Yoo-hoo, and he drank it. Okay? Well, heat, the main ingredient in gas line antifreeze, is methanol. It's toxic to you. And so, one treatment for accidental ingestion of methanol used to be to give the patient ethanol. Why? Because this enzyme, this alcohol dehydrogenase, given the choice of methanol or ethanol, that enzyme likes ethanol more. And so what the doctors would do is they would give ethanol so that the patient who had accidentally drank the methanol, they would remove the methanol by dialysis. And so the overall process, y'all, the reason methanol is toxic is because formic acid. Okay, if you let this whole process happen and produce formic acid, it could kill the person. But if we just literally get the toddler drunk, okay, give them some ethanol, we can then use dialysis to remove the methanol from the blood. But do you see that treatment, guys? That treatment was known because this process had to be figured out. Kinetics had to be studied. It had to be realized that the enzyme, alcohol dehydrogenase, likes ethanol, I think the book said 100 times more than it likes methanol. That's why the process works, is understand the kinetics of it. Now they actually do not use that treatment. I was reading in the book, there's a drug for it, okay? So, along those same lines, talking about drugs, this is another story from your book. And I don't remember what year it was, I think it was the 90s. This pharmaceutical company had developed a drug, and their goal was to use this drug to treat parasite infections. And before the drug was marketed, naturally they went through trials. And some people took the drug for the parasite, some people took a placebo, right? Just a sugar pill. And then they had these people take the drug, and of course, you know, they're monitored symptoms, etc. Well, the people that took the drug, it did work actually to get rid of the parasite, but the people noted that every time they drank alcohol, they got really sick. And I don't mean like a drinking binge. I mean, y'all, just a little bit of beer or a little bit of wine, and they got really nauseated from this drug. And so the company looked into it, and what they found is the drug, yeah, it would treat the parasite, but the drug was, was stopping this second enzyme from working. Well, the reason they were getting sick is because of the acetaldehyde buildup. That's what builds up that makes you sick from drinking alcohol. Okay, and it was an unknown characteristic of the drug. But because of that research, they decided to market that drug also as a treatment for alcoholism. And so people who struggled with, with alcoholism, they would take this drug, and as soon as they drank a little bit, it'd make them sick. And hopefully that's a physical way to make them stop when they can't mentally overcome their addiction. So that's just really cool, fascinating application of chemical kinetics. Okay? Now, there are 4 factors that will affect the rate of a reaction. One of those is the states of the reactants, or like surface area, if you will. By states, I mean like solid, liquid, gas. Y'all know gasoline burns, yeah? Flammable. I'll bet you also knew that it's the vapor that burns. right? The vapor is what ignites, it's not the liquid. Think about, what the states of a liquid versus a vapor have on surface area. Which one has more surface area? The vapor. It's gas particles. And so it's almost as if every particle can be attacked at all angles. But a liquid, you're only dealing with the surface, right? As far as flammability. Kind of along those same lines, when we're talking about surface area, if you have a headache, take an ibuprofen. Have y'all ever used Goody's headache powder? Okay. You ever heard of it? No? Okay. Well, here you go. Goody's headache powder. It's just like it says. It's a powder. Does it make sense to y'all that if you take a powder, your stomach's going to be able to process that quicker than it would a tablet? Okay? And so you can get quicker relief from the headache. Now, you're going to taste it too, right? Because it's a powder. So you got that to deal with, and most of us just would rather swallow it and never taste it, okay? But, that's what it is. If you increase the surface area, you can increase the rate of the reaction because the reactants can see each other more readily. Another factor that would affect rate, and it kind of goes along with the states, is going to be the concentration. Does it make sense to y'all that if you react things that are more concentrated, they're probably going to react faster? Because in order for a reaction to happen, don't we need, like if we're saying A plus B makes AB, in order for that reaction to happen, A and B need to bump into each other. And the more concentrated it is, the more likely they are to bump into each other and cause a reaction. Okay, now it takes more than just bumping into each other. There's energy to overcome as well. Okay? The third factor that could affect the rate is the temperature. If you increase the temperature, you increase the rate. Why would that increase the rate? Tell me on a molecular level and based on what other stuff I've been saying. What's temperature going to do on a molecular level?
It would increase the solubility of a solid.
Okay, it would increase the solubility of a solid. What about when we're talking about molecules colliding and how often they collide?
It speeds them up.
It speeds them up. Yes? So do you see that as you increase the temperature, the molecules are moving faster? A, they're going to collide more often. B, they're going to collide with more energy. Okay, and so there's more likely going to be a reaction. So usually if we warm things up, the reaction happens faster. And the example I always think of is, y'all, if you have milk in your fridge, it's going to sour over time. But that's a case of where we're lowering the temperature to slow down the reaction, right? If you leave it on the counter, it's going to spoil a whole lot quicker. Okay, so you can clearly see there how temperature affects the rate. The fourth factor would be a catalyst, okay, which is, we've been talking about that a lot with my stories about the methanol and the ethanol. Do you guys remember from biology or something what a catalyst is? We learn in biology that enzymes are catalysts.
Like carry something?
Okay. Catalyst speeds up a reaction without being used up. And like, y'all have heard terms glycolysis, Krebs cycle, citric acid cycle. Y'all, those processes would not happen if it weren't for enzymes. Enzymes, they do a lot. And how they work, it depends. Different enzymes work differently. Sometimes what an enzyme does is it grabs the ethanol and it literally holds the molecule so that it can react a certain way. Okay, sometimes it grabs the molecule and it's ripping it apart. Okay, but catalysts speed up a reaction and they themselves aren't used up. Y'all heard of a catalytic converter? Where's that?
Core.
In your car. What does it do? Huh? Catalytic converter?
How the catalytic converter goes in your exhaust when keeps your from being too loud. Take them out.
Keeps your who?
Keeps your exhaust from being too loud.
If you take it out, the exhaust is loud. Yes, but there's a chemical thing going on there too.
It like is better than
It's
the
got
Yes.
platinum and it's got some.
It's got platinum in it, yeah.
And it's got something else that's going for a lot right now. We still not what's called.
Yes, do you know kind of
Eroded?
It's platinum. It's platinum in them. My husband, his home place, this happened, y'all, just last, I can't remember if it was last summer or if it was in the fall. His home, nobody lives there. It's in Okolona, etc. There were some high-class people that would come and pilfer through the barn and stuff, and they took the catalytic converter. They got under the vehicle that was there and stole it. And anyway, it's really frustrating when that happens
Oh,
too.
yeah, this is something else when it goes for like 11,000 a pound, and people will just get it, this little triangle thing that cuts into them, they crack it open and just.
That's
pour it
in the
out.
catalytic converter?
Mhm.
Okay, I knew there was platinum.
Mine
Is it
was,
a,
I think it's, for some reason, I'm thinking palladium.
palladium? Okay. And it could be it's palladium, not platinum. Maybe, I thought, yeah, Google that, Cameron, and tell us what it is. But a catalyst takes your exhaust and it controls your emissions, is what you were saying, Paul. Yes, that's the purpose. People do remove the catalytic converters from their vehicles to make them sound louder, because apparently that's cool. And it's you gotta be careful, because I don't think there's, in some states would have laws
Oh,
against
yeah,
that.
you, some states you'll get.
Yeah. Probably California. They're not gonna like that. Have you found that?
I'm trying to get on the Wi-Fi.
We were complaining about that just a few seconds ago. Okay, so that's the factors that affect the rate of a reaction. Now, let's talk about how you measure the rate of a chemical reaction. Rates are going to be measured in a change in concentration over a change in time. So I've kind of written that mathematically. What does the triangle mean?
Changing.
Change in. You're right. Thieves target catalytic converters because they contain precious metals like platinum, palladium, or rhodium. So you're right. Okay, so the triangle means change in. Y'all, these square brackets here, that's a way to express concentration. So if I wrote this, I'm saying concentration of hydrochloric acid. Okay, and I don't know if I've introduced y'all to that before, the square bracket
Is it
thing.
like molarity?
Okay, a lot of times it is molarity, yes. When we're dealing with gases, instead of reporting like the molarity of hydrogen, typically that would be reported in terms of pressure. Okay, like the pressure of hydrogen is this, is how we do gases. And of course, when I say over delta T, it means over time. And what units are used, kind of like what you're asking, whether it's molarity or whether it's atmospheres, it depends on your reaction. Likewise, the time would. If a reaction happens really fast, then most often we'll see, molarity per second, yeah? But if you're talking about, like we were mentioning earlier, iron rusting, it might say molarity per day. Or it could even do years when you're looking at certain radioactive isotopes. That can be reported in weeks or years, but any kind of unit of time. But that's what rates are going to look like. And we'll encounter some different rates over the course of our calculation. So think about your journey to school this morning. And I asked you how fast you drove. Y'all, you might give me an average rate over the whole course of your journey here. But if I could pick just one instant of your journey, I might find y'all stop at a stoplight. And it looks like you're going 0 miles per hour, okay? So again, just rates that we're familiar with in practical terms, it's a distance over time. With chemical reactions, it's a concentration over time. It's how we would do a rate. Likewise, I might ask how fast you drove, and if I caught you going down 82, it might have been like 80 miles per hour. Okay, that's like me talking. It might have been 85 at some point because I just get so excited about getting here. But the same, when we're thinking about that process, y'all, you can't take a chemical reaction and look at a certain point to get the rate because it's not, you can do that, but do you see it's not necessarily going to be accurate. And also, as a chemical reaction happens, you start with a whole bunch of A and B, and as the reaction progresses, A and B are getting used up. So typically rates slow down over the course of a reaction. So keep in mind there are different ways to measure rates. Usually what is measured is something called the instantaneous rate.
I remember this from physics,
Do you? Oh,
high school physics.
okay, wonderful. It's nice when things come back around in full circle on each other. And so, for example, if you were measuring like the concentration of A over time, over the course of a reaction, y'all typically, this is not a linear plot, but typically the concentration of A drops over time like so. Okay, it's a curve. The way we get an instantaneous rate is we could measure a whole bunch of little bitty points all along that curve, but, and this might be where you're getting from physics, it's easier to measure just a tangent to the curve. And that's where instantaneous rate comes from. It's the tangent to the curve, okay? And it's like an average, but we don't use the word average. We use instantaneous, okay? Also, you could measure, like this is some data here for the reaction of bromine, Br2, it tells you in this, with formic acid. And I would have to look up the... Okay, it's some data for this reaction. And so what's monitored for this data, do you guys see, it's the bromine concentration. And look, as the time progresses for the reaction, what's happening to the concentration of bromine over the course of the reaction? It's going down, right? It's getting used up. Look at the numbers for rate over there. See, that rate is molarity per second. What's happening to the rate? It's getting smaller. So do you see, if you measure a distinct point in time, you're going to have different rates, but we would be looking at an instantaneous rate instead. Okay? Something else about rate is that the rate of a reaction follows the stoichiometry of the reaction. For example, if I write AA plus BB yields CC plus DD, that's my chemical reaction, that's just generic. Y'all, what do the lowercase letters mean?
Moles.
Okay, they're moles. The lowercase letters are your coefficients. Yeah, they mean the moles. Do you see that the uppercase letters represent the components, the hydrogen or whatever? Okay, so if we were talking about the rate of a reaction, this is how we would write it. That 1 over A, that's the coefficient, times the change in concentration of A over change in time is equal to 1 over B, there's the coefficient, times the change in concentration of B with respect to time is equal to 1 over, that's a lowercase c, okay? And this will be clear and simple in a moment. Hang in there with me. What I'm telling y'all is that the rates of all the components of a reaction are going to be related to their stoichiometry. Like A and B aren't necessarily going to be disappearing at the same rate unless their coefficients are 1 and 1 or 2 and 2, unless they match. Also, let's talk about that little triangle, change in. Change in means final minus initial. Yeah? Think about your reactants. Final reactant concentration minus the initial reactant concentration. Do you see that for a reactant, the final minus initial is going to be a negative number? Okay? So a lot of times when you see an expression like this, like I have written, you'll have negatives in front of the reactant expressions because, y'all, you can't have a negative rate. The negative means it's getting used up, but you don't drive negative 30 miles per hour. We use the signs to denote direction, if you will, okay, or that it's getting used up. So, if I said 2A plus B yields 3Cs, and y'all, I'm going to give you a rate for B. And we're just going to stick with whole numbers to start. If I told you that the rate of B is 5 molarity per minute. Okay, so B is being consumed at 5 molarity per minute. How fast is A being used up then? Take a guess.
Twice that?
Yes, twice that. The answer is A is getting used up at 10 molarity per minute. Do you see how you do that? Okay, how you would write that expression, like I did at the top, we would say for A that 1 over 2 times the change in concentration of A with respect to time is equal to the change in concentration of B with respect to time. Now, what's along with that B, I'm going to write it in red, then I'm going to erase it. It's a 1 over 1, isn't it? Because the coefficient of B is 1. When I give you the 5 molarity per minute, I'm giving you this. I'm asking y'all for what's happening to A. This is what I'm asking for. So do you see that half of what I'm asking for is equal to 5 if we plug numbers in? Or I would cross multiply. So in other words, the change in concentration of A with respect to time is 10 molarity per second. Okay, that's one way to think about it. And that one was an easy one to do in your head, yeah, because it's 1 and 2. So what if I asked you, I said B is getting used up at 5 molarity per second. How fast is C being generated?
3 times as much?
Mm-hmm. It's kind of like a stoichiometry. Wouldn't you have to say, where am I going? Times 3 divided by 1? So C is being produced at, I'm sorry, I changed my units to seconds down here. I'll stick with minutes. C is being produced at 15 molarity per minute. Okay? Do you likewise see, y'all, that in this example, I'm giving you the balanced equation and y'all are using the coefficients to calculate the rates of everything. But do you see the flip side of that? I could give you the rates of different components and you could figure out the stoichiometry from the rates by seeing how they relate to one another. So if you don't know the structures of what's reacting, if it's a new process that you have discovered, you could figure out how the ratio of the reactants and products work based on the rates. We okay? Now, that is section 1 of chapter 14. You can kind of start looking at some connect. Okay, I mean, or not.
I miss a lot.
Huh?
I miss a lot.
No. Hang on, let me stop this recording.